We're good. Oh, yeah. Hold on. You're muted.
There you are. But anyway, visit with you later.
Okay. Am I?
Go ahead and
Hello, GLPA+WACins. Usually I would say hello, GLPins, but we have some WACins here today too. So hello, GLPA+WACins. Welcome once again to our giant screen theater. Today we have an invited talk by artist Herrold, and I will introduce artists in just one moment, but I do want to mention two small logistical things. So the first thing I want to mention is that if you looked in your bag of nice things that we were supplied with by some of our sponsors that you got when you checked in, thank you, sponsors, but also your conference gift was in there, and you might be aware that GLPA conferences, typically the host has a little item for you to take home and remember the conference by. And our conference gift was a sticker sheet that was designed by Emily Romy. And so don't miss it because it might look like a piece of paper, but it's actually stickers, and I think they're kind of cute. So I hope you like them, and that's your conference gift. It's in your bag of goodies. And then, thanks. Yay! And then the other thing I wanted to mention is that on Friday, there are slots available for resume reviews by professionals from Bradley University's Smith Career Center. And I want to encourage you to sign up for a slot. There's 15-minute slots available. There's a link on the website. And you might think, I'm in my job, I'm stable, I don't need my resume reviewed. But what if you're applying for a grant and you have to supply a resume? Or what if a new opportunity comes up? You should always have a resume just ready to go. So I'd encourage you to please sign up for some time slots for those resume reviews if it fits in your schedule on Friday morning. Okay, now let me introduce Ardis Herrold. Ardis Herrold is the education specialist for the Vera C. Rubin Observatory. She is responsible for designing and testing the classroom investigations and teacher support materials that will make use of Rubin data once it becomes available. Ardis also leads teacher professional development efforts and oversees the Rubin Observatory Educators Community of Practice. And she is leading a workshop on some of these materials on Friday morning. Prior to joining Rubin Observatory, Ardis taught physical, earth, and space scientists at the high school and college level. She also worked in various planetariums and was a member of the Great Lakes Planetarium Association. and manage night labs and observing nights for students and the general public. A lifelong amateur astronomer, Ardis has a personal observatory near Tucson, Arizona, where she images deep sky objects, comets, and supernovae. Ardis has a geology degree from the University of Michigan and still enjoys collecting rocks and minerals. Have you seen our amethyst yet? I'll show it to you. She also loves hiking, biking, and playing drums and guitar. Let's give a warm welcome to Ardis Herrold.
Thank you, Renee. I have my own. Well, hi, everyone. I'm really glad to be here. And it's been like 7 or 8 years now since I've done a planetarium show, but it's great to reconnect with a lot of old friends and meet a lot of new ones. So I wanted to give you just a little snapshot of my astronomy journey. I fell in love with astronomy in 3rd grade when Mrs. Ives taught us the constellations. I made a personal connection with the sky because I went out and saw Orion. I lived in a small town. It was dark enough for me to see the stars. And it just like launched me into a lifelong passion for astronomy. I went to the University of Michigan, starting in astronomy, ending in geology. And then after that, I taught for almost 40 years in the Southeast Michigan area, various places. Out of those 40 years, or 38 years, about 30 of them was working as a part-time position for our school planetarium in Grosse Pointe, Michigan. I've also worked at several other planetaria along the way. When I was in Grosse Pointe, where I spent the most of my teaching career, I also created and advised a group called the RATS, the Radio Astronomy Team. So I have quite a passion for radio astronomy, and that's another story. But in 2017, I accepted a job at Rubin Observatory to lead the education program. First of all, to design an education program, and then to lead it, and that's where I am today. You can see a few pictures here of my personal observatory in Tucson. If you're ever in the area, contact me, and let's go out and visit. So I'm going to tell you a story today that kind of context why we have a Rubin Observatory. And that story started back in the 1990s, when Tony Tyson and Roger Angel were kind of musing, sort of like peanut butter and chocolate, about what we really need in terms of an astronomy instrument for the next decades. And one of the problems that Tyson recognized is that we needed a lot more data to have better insights into dark matter, and then hence dark energy as well. Roger Angel, who many of you might know is a very gifted optician and worked at the Mirror Lab in Mirror Lab in Stewart Observatory in Arizona, designed about dreaming this really wide field, fast-moving, deep imaging optical telescope. And so the two of them got together and started talking this up with white papers and talking to various people. And said, you know, the real reason we need this telescope, which at that time was called the Dark Matter Telescope, was to help us understand what a lot more of the universe is like compared to what we can see with our eyes or with optical instruments. And the very first mention of this in the literature was in the late 1990s, but then many of you are familiar with the decadal surveys that come out every 10 years that kind of set the story for what our nation's priorities are going to be in astronomy and astrophysics. And this telescope was first mentioned back in the 2000 decadal survey. It was renamed the Dark Matter Telescope from the Dark Matter Telescope. It was renamed the Large Aperture Synoptic Survey Telescope to make it more descriptive of those factors I just mentioned to you. So wide, fast, deep is the quick way to think about our telescope. And there wasn't any instrument like that on Earth at the time. Things take a long time to happen. So starting in 1996, we move forward now to the middle 2000s, where we started a corporation to start collecting grants and soliciting private donations. Charles Simoni and Bill Gates collectively tossed in $30 million to begin the construction of the primary mirror, and that's kind of what got us kick-started. In 2010, the next decadal survey this telescope was named as the top priority. So at that point, a lot more funding was channeled our way, not only from the National Science Foundation, but from the Department of Energy, which invested money in building the largest camera ever made for astronomy, and I'll tell you about that in a few minutes, as well as private donations through the LSST Corp, which is now called the Discovery Alliance, if any of you are looking for it on the internet. So we started construction in 2015, and in 2019, it was renamed the Vera C. Rubin Observatory. And I don't know how much all of you know about Vera Rubin. I personally did not meet her. I'm sure there are people here in the audience who met her, was tutored by her, heard her talks. But anyway, Rubin was one of the primary scientists who established evidence for dark matter in galactic halos. She did not come up with the idea of dark matter. That happened decades before, but she gave a lot of credence to the idea with decades of observations that supported that idea. And so we also wanted to give credit to Vera Rubin because she was bypassed for a lot of major science awards, probably because she was a woman. We can only speculate on that. I would like to show you an example of one of our 2-minute animated videos that we've made at the observatory that introduces you a little bit more to Vera.
Why is our observatory named in honor of Vera Rubin? Dr. Vera C. Rubin was an accomplished American astronomer who provided convincing evidence for the existence of dark matter. How did she do it? Using a new technology, Vera worked tirelessly to observe and record the behavior of galaxies. Her data showed that some unseen matter must be out there, affecting how fast galaxies rotate, and that this dark matter makes up most of the matter in the universe. Vera Rubin's work had a huge impact on astronomy, and it inspired the design of Rubin Observatory, which is carrying on Vera's legacy by helping us learn more about dark matter. But Vera Rubin's path towards transformational science wasn't easy. Many people discouraged her from doing science, saying that being an astronomer was not a woman's job. Vera did her research at a time when few women could even access telescopes, and observatory buildings didn't even have women's restrooms. But Vera believed that anybody who loved the stars should be able to study them. Vera Rubin once said, "We all need permission to do science, but for reasons that are deeply ingrained in history, this permission is more often given to men than women." When Vera saw examples of this inequality, she wrote letters asking editors, professional societies, and influential scientists to provide more opportunities for women. She also supported astronomers who were just beginning their careers. She invited graduate students to collaborate with her and insisted that their names be listed as co-authors on publications. She attended their talks, included them in social gatherings, and asked questions about their research. Vera Rubin once wrote, "It's all right to be charming, gracious, brilliant, and to be concerned for others as we make our way in the world of science." We at Rubin Observatory want to carry on this legacy of helping everyone join in the fun of discovery, regardless of their age, gender, or nationality. We welcome you on this journey, just as Vera herself would.
Okay. Now I have to figure out how to get back into slideshow mode here. Okay. If you hit escape. Slideshow, got it. Thank you. All right. I don't know if you all heard about this, but there's a quarter coming out in next year in the science series, and Vera Rubin is going to be on one of those quarters. She has a lot of different things named after her now: a ridge on Mars, a crater on the moon, a data center that's getting named after her, a satellite, an asteroid, but now a quarter. So did you know that there was a Vera Vera Rubin Nebula in Star Trek Discovery Season 3. So Rubin Observatory is in Cerro Patron, Chile. It's in the Andes foothills, where we have a number of U.S. and international observatories. You can see the position in terms of altitude and latitude there. I myself have never been to the observatory. I'm soon going to have a chance. I'm very excited about that. But we have a lot of observatories in Chile, first of all, so we can observe the southern hemisphere sky, but also some of the best atmospheric conditions in the world. Very stable, very dry, still relatively dark compared to many of the other places. And in addition to that, the government of Chile is very happy to work with us and provide infrastructure and citizens who want to be involved and work at Rubin Observatory. And so the infrastructure is there not only in terms of the governmental support, but also in terms of what we need for the technology. And so those are a few of the reasons why we selected Chile as the site for the observatory. And you can see its location here. It's north of Santiago. Kind of, if you imagine Chile, which you know is a very, very long country in South America, it's a little bit above the middle, if you will. So you probably noticed that our observatory has an unusual shape. People describe it like a shoe or many other things. And that is so that we have all of the things we need in one place. So as you can see in this breakout, we have a machine shop there. We can recoat the mirror there. We don't have to take it out and transport it somewhere else. And so everything is there for us in one place, and that will save a lot of time and efficiency as different kind of upgrades need to be made, or the periodic cleaning and recoating of the mirror. The telescope is also, as you'll notice in the next pictures, built into the mountain somewhat, so that's kind of a neat feature of it as well. So our telescope is actually not called the Vera Rubin telescope. Our observatory is called Vera C. Rubin. We prefer you don't say the. Vera C. Rubin Observatory. This telescope is actually named the Simoni Survey Telescope. And in fact, Charles Simoni just had his family down there earlier this month for the official dedication of that. So this is a more recent picture of what the telescope looks like now. One of the things you'll notice about this telescope is it's very short and squat. That compact, lightweight design allows it to move very, very quickly. Also notice behind here the size of the slit. We have a supersized slit, and that's because once the telescope starts taking pictures at the rate of 1 every 30 seconds with a 5-second time to slew and settle to the next image, the dome has to keep up with it, and what we have is what's called a crawling dome. It never stops moving when the telescope is imaging. It just is constantly going from one image to the next, and because that dome has to be in the position for the whole 30 seconds of the image, it's wider than most telescope domes so that it doesn't start moving off of the image. So just a short video here to show you the design for speed here. But this was a video from a few years ago, but you can see it can move very, very quickly. I'm told that it can slew faster than you can run, but I don't know what the exact speed is. This allows us to take many, many images per night, and we'll talk a little bit more about that. The telescope primary mirror was made at the University of Arizona Mirror Lab, and it's a very unusual mirror because of its optical surface, but like many big mirrors, it's a honeycomb design that allows it to be very lightweight. It allows it to be manufactured and ground much more quickly. And this is a picture of the mirror before the grinding. But what's interesting about it is it has two reflecting surfaces. It has an outer ring that we call the M1, the mirror 1 ring, and then it has an inner ring that's more steeply curved called the M3 ring. And as you can see how this works, the light is coming in, hits M1, reflects back up to the secondary mirror, mirror 2, reflects back down to the tertiary mirror, mirror 3, and then up into a series of lenses and into the camera. And that allows us to keep the telescope mount short, and it allows us to build the dome smaller. Just a whole lot of things that help not only with the motion of the telescope, but also the cost and the construction. You might wonder, why did we pick an 8.4 meter diameter mirror? Well, there's this tunnel that you have to go through. Once the mirror gets off the ship and gets trucked up to the mountain, and they're literally just inches on either side of clearing that tunnel. So we really could not have built a bigger mirror than this particular size. We just recently coated the mirror in April, and this is really pretty cool if you have not seen this. And there it is. You have to look at this picture carefully to figure out what it is you're looking at first. So an interesting thing about that is 8.4 meter mirror, the amount of silver applied was about the same amount as a cherry tomato. Okay, so not very much silver, but very, very nice thin coating. Nice job, it worked great the first time. We practiced a lot, so that's good. Now, in addition to having this wonderful, unusual mirror, we have the largest camera ever built for astrophysics. The LSST camera, or sometimes called the LSST cam, is about the size of a Mini Cooper. It operates at about minus 100 Celsius. As you can see here, pretty significant weight to hang above that telescope, and it has a 6 filter changer, and as we go through the sky every night, we're imaging in 2 different filters per night. And that's what it looks like in terms of, you can see some people in this picture to give you some kind of sense of scale for LSST cam. Here, the camera filters go from ultraviolet to infrared. Near infrared doesn't go quite as far as like Euclid does, but these filters are able to be changed off in just a few seconds. And with that, we have 2 Guinness World Records with this observatory, one for the largest optical lens ever built that you see in this picture, and the other for the highest resolution camera. So every image is 3,200 megapixels big. And you see a fun fact here, if you took all the people in the United States, China, and India combined and make each person a pixel, that's about how many pixels are in one image. As I mentioned earlier, the camera was built by the Department of Energy at the SLAC National Accelerator Lab, and here's a picture of the crew who just finished the camera before we shipped it off to Chile. The images produced by this camera are very huge. If you think about Orion's belt, they're just a slightly larger diameter than Orion's belt. So they're very large compared to a typical telescope, or if you think about the area of one image, it's about 45 plus full moons. So we're grabbing a lot of sky every 30 seconds when we take these images. And because the camera images are about 100 times larger than a similar telescope that is equipped, we can do in 10 years what another telescope would take 1,000 years to do. So you can see we're building toward grabbing a lot of data. How do you visualize that? Like, what's the resolution? Well, if you took 378 4K HD TVs and lined them up side by side, then you can display one image at full resolution. You know, we have people like, well, when can I download an image and use it on my computer? Don't understand the concept of these images. Think about that, about a little bit bigger than half of the size of a basketball court to display one image. Not only do we have these very large images, but they go very, very deep. So on the left, you see a typical image from the Sloan Digital Sky Survey. On the right, a simulated image that will come off of our telescope. So you can see we're going to be much deeper looking at things. Our initial snaps will be magnitude about 24.5. We saturate at magnitude 17, so we can't see anything brighter than that. So effectively, anything you see in the planetarium or night sky is too bright for us to collect data on. So we're going very deep into the cosmos. And with that, we're going to be able to develop just millions of images and find billions of objects. So a lot of people talk about the data coming off of our telescope as drinking through a fire hose. Well, I myself have never tried to drink out of a fire hose, but I did go to Iceland this summer, and here's a picture of me standing by one of the waterfalls, and you can see I'm a pretty significant distance away, but I'm just in the spray of this waterfall, and I'm absolutely soaked. Now imagine getting underneath that waterfall, opening your mouth and trying to ingest what's coming off of that mountain. And that's kind of like what the issue is with what we are going to be facing, both scientists and anybody else who cares to look at that data. So 20 terabytes of data every night. So if you have a MacBook like I do, you'd need about 40 of them to store one night's worth of data. So downloading into your computer, not going to be happening that way. Or think about it this way. The amount of data in one night coming off is like streaming Netflix, binge watching it continuously for 3 years. No break. Or streaming Spotify for 50 years. Now, those of you who are older than 50, think back 50 years ago how old you were. Next year, I'm going to be going to my 50th high school reunion. So basically, from the time I graduated high school till now, that's how much data would be flowing. I'd have to be listening to music continuously throughout my life. And that's one night. So it's really hard. And this is one of our challenges is when we start talking about this to our audiences, how do you convey that this is not just another telescope? It doesn't do things in the same way that other telescopes do things. And so we have to think of equivalencies or analogies that help our audience bridge to have some kind of understanding of that. And so another interesting fact you can see here, I tried to load this talk up with a lot of talking points that you might be able to use in your planetarium, in your classroom, in your museum, that if you took all of this data and digitized it, it's more than all language has ever been written in all of human history. And that's just the first 10 years. We hope the data will keep flowing after then. Or here's another interesting one. First week of operation, we will have more data than Hubble ever has collected. I say Hubble, not Webb, because I think more people are familiar with Hubble, okay? So, or it would take 120 years for Hubble to image the sky just once compared to what we will do in 3 nights. Now, some people are fascinated with this data, so I wanted to just take a few minutes to explain it. It's coming down from the mountain. We have a base facility in La Serena, which is about an hour away, probably 2 hours if you're talking about drive time. We have a redundant fiber optic system that goes on either side, basically, of the continent back to our data center at SLAC. SLAC will do the initial processing. It will generate what we call alerts, which are changes in the sky. And we split our data processing between SLAC in California, between the UK, and between France. So we have partners that will be handling a substantial amount of our load. And our headquarters is in Tucson, so that's where I live and that's where I work, because I'm not a scientist that has to deal with being there at the mountain. But if you think about it, what we're talking about is trillions of measurements on billions of objects. So if you wanted to study something, like maybe asteroids is your thing, you have to have a way to sift through that data and get what you want. And that's a real challenge for us. So what we have are what we call downstream brokers. We have places where you can, there are software packages where you can go to filter the data and to get what it is that you'd like. But again, talking about the data flow, people don't understand like how much data is coming in every night. And so, I've talked to amateurs and they're like, well, I want to see what supernovas are going to be rising in brightness so I can observe them with my telescope. Well, we're going to get thousands of supernova a night, so how are you going to filter that and, things like that. There's a lot of interesting issues. So this whole 10-year survey that we're going to begin next year is called the Legacy Survey of Space and Time. And the reason it's such a long name is because we had the LSST named the Large Synoptic Survey Telescope for a very long time. And when we renamed our observatory Vera C. Rubin Observatory, we didn't want to let go of the logo. We had so many things that had LSST smeared all over it. So one of our data scientists cleverly said, well, let's adopt the logo for the survey. And that's where we came up with this name. So I'm not going to read this to you, but you can get a feel for how many objects we're going to be collecting, 4 to 5 times as many objects as there are people on Earth in the first 10 years. Now, why are surveys such a big thing? Surveys have been going on for a very long time. But what a survey does is it allows you to see patterns that maybe you would not have seen if you only looked at small areas of the sky. It allows you to see patterns that happen over time. The more often we observe the sky, the more likely we are to find things we never knew about. And the idea of the survey, going back to Dr. Rubin's kind of legacy of being inclusive, is we wanted to provide data for all sorts of scientists, not just one kind of scientist. And so I'd like you to play a game with me right now. Get your phone out, scan the QR code, or put the link in your computer if you want. And I want you to play Space Surveyors. It takes 1 minute, start whenever you want. And we'll see who can get a high score. This is a game we developed to try to explain the concept of a survey telescope. It's something you might be able to use in your setting, whatever that might be. And it's kind of interesting because as you play the game, you have to think about, well, how am I going to avoid clouds, airplanes, where the moon is? And all these things had to go into thinking about what we call the scheduler, the way that we take pictures in the sky. We're not just going up and down in the sky. We can't do that. We have to think about where the moon is, what phase it is, and what filters we're using that night. So there's a lot of different things there. What'd you say? Starlink. Yeah, Starlink. Well, Starlink is one of many satellites, right? There's many of the constellation satellites now that are causing issues. So they definitely will affect our data. We're working with the companies to try to mitigate as much as we can. I could talk more about that later in questions if you'd like to. I'm still listening to the music. I figure you're done when I don't hear it anymore. Anybody get about 20? Anyone get over 25? 25? What did you get? 28. Anyone beat 28? What did you get? 31. Awesome. Anyone beat that? You're the winner. All right. Well, I hope you enjoyed that. So I wanted to talk to you about an analogy I use a lot because I think it makes sense to people. I like to make jigsaw puzzles. I mean, some people hate them, but I love them. Now, imagine that the universe is a jigsaw puzzle, and we have about 10% of it done. Maybe in some areas of science, 20% of it done. When we get done with our 10-year survey, we'll have 80% of it done. So I found a website that only sells web image jigsaw puzzles. I hope they shift that to Rubin in a few years. But imagine if you could only see 10% of this image, could you really understand what it is you were looking at or see connections? And now imagine if you saw 80% of it, wouldn't you have a much better idea? And this is what scientists are so excited about. They're going to have a lot more pieces of the puzzle, whatever puzzle they happen to be working on, solar system or galaxy or dark energy. They'll have a lot more pieces of the puzzle than they've ever been able to achieve before. Now, we're imaging the southern sky primarily, but we're also going into the northern hemisphere a little bit to get the ecliptic plane. So we're imaging solar system objects as one of our big science areas. So you can see kind of the concept of the survey here, and the colors show you over 10 years how many images we'll be taking of each area of that sky. This is really kind of a curious thing. I don't know if any of you look at websites like where planes are flying at any given moment, and it's kind of mesmerizing. But what you're seeing here is a simulation of the survey cadence, like every night, how are the images being taken? Where are they being taken? What filter? The colors show you the changing filters. And then on the right-hand side of the screen, you see cumulative sky coverage over time. So scientists and engineers have been discussing this for years and years, and everybody wants something slightly different to optimize their science. So this has really been a worldwide compromise, and it will continue to be a dynamic compromise. So as new things get discovered, as different kind of issues arise, we will be able to quickly change our software to be able to do this. So this is a fully automated process that goes on and on and on and on every clear night. Our 4 main science goals at the observatory are to understand dark energy and dark matter better, to build a better understanding of our solar system, to build a better understanding of our Milky Way, but also the local environment around the Milky Way. And then finally, and this is what we're really optimized for especially, is exploring things that change in the sky. And so let's talk about dark energy and cosmology. I'm going to give you just a few examples of each one. We can use gravitational lensing, and we'll collect way more lenses that have ever been imaged before to understand the kind of filaments that exist in the universe and the halos that might exist around galaxies and galaxy clusters. We can use that lensing to map out not only where dark matter may exist in the universe, but also where it existed in different eras and how it evolved over time. In terms of the Milky Way, this is a simulation of, how galaxies form. And the Milky Way will be one of many galaxies that we'll be imaging over time. And out of these 20 billion galaxies, we'll context our galaxy in a local environment in terms of what we're building on a very large structure map. Things like stellar streams will be much more easily identified. We'll begin to get more insights into the evolution and formation of our galaxy. In terms of what changes in the sky, both in brightness and in position, we're going to see a lot of supernovae. That's one thing that people are very interested in. You can see here 2 images, day 0, none detected, day 128, how many supernovae we've detected at that point, just in that little sky snapshot. But besides supernovae, there are many different things that change in brightness. And some of them are kind of interesting, like is there optical transients that are associated with gravitational wave events and things like that. They aren't all just variable stars and supernovae and such. But with these supernovae, we're going to be able to map out more accurately cosmic distances. And so we'll get a couple thousand a night. out of those few thousand, will get some type 1a supernovae every night. And using those type 1a supernovae, we can use those as standard candles to better define some of the distances in that part of the universe. Our solar system is another area that's going to be really interesting. So we're optimized to find dim things that move slowly and things that move quickly, because we'll have this long survey, but we'll be taking pictures every 3 days, and we'll take them in 6 different bands. So one of the things we'll be very, very good at is picking up near-Earth objects, and I'll talk more about that in the next slide. But these are estimates by the end of the survey, and I will tell you that these numbers are much, much bigger than how many objects we know about now in our survey, in our solar system. You know that so far we've found 2 interstellar objects cruising through our solar system. We think, and these are just estimates, that we'll probably grab about 10 by the time we're done, about 1 a year. In 2005, there was a mandate put out in the United States for us to find 90% of all near-Earth objects that were larger than 140 meters across. You might know they're called potentially hazardous asteroids. And we've done a really lousy job of being able to do that just because we don't have the technology to keep up with how we need to survey it. But we hope that once our telescope goes online, especially in the first couple years, we're going to get up to about 80% completion of that. So that's going to be really interesting. And then what about the far solar system? TNOs, KBOs, Planet 9? What else is out there that we don't know about? Because so far, it's been too slow moving or too dim for us to detect. And so we're going to find out a lot of things about all these areas of science. And in addition to that, we're working with other telescopes at observatories and sky surveys to do what's called multi-messenger science. So looking at different aspects of data coming in on objects. So not only do we have the photons coming in, but there are neutrinos, there are gamma rays, there are gravitational waves. Combining all those to study one object is a really important new part of what a lot of our science is pointing toward these days. And then we have targets of opportunity. We find something that happens at another observatory, and they say, hey, can you look at this very quickly? Oh, yes, we can. As long as it's in our part of the sky, we can do that. We can pivot off of that computing algorithm in just minutes and look at this target. And so this is going to be really exciting. In addition, flip it around, we're going to find things that nobody else noticed, and we're going to ask other observatories to do follow-up observations. Okay, I'm going to take just a very small amount of time to talk to you about our team, because I want to get to some of the more interesting things at the end. So I'm part of the Education and Public Outreach team. That's how many of us there are. Many people think there's like 30 people working on this project, but there's like 9. And so we are actually the public-facing group that brings astronomy to you, to the public, and helps scientists also facilitate communication. So we build the website, which is mobile-friendly, by the way. We have an extensive gallery, and of course that gallery will get much better once we start pulling images off of the sky. We have a series of animated videos, and I'm mentioning these things to you in case you're looking for resources. If you're going to build a program about talking about Rubin, like what do you have that you can go to right now on the website and get? We have a very aggressive social media campaign. Some of you are probably followers in different facets of it. And in addition to that, we have an education program, and that's the part that I work on. And so we have adopted that wide, fast, deep mantra for education. Wide, meaning we want it to be very inclusive for most students, not just the really involved, like high-level research kind of student. We want it to be fast, so you can go through an entire investigation in your classroom in a couple hours, and very low learning curve, no tools that you have to learn, nothing you have to buy, nothing you have to install, nothing you have to download. If you want to know more about that, come talk to me Friday at the workshop. And then deep, we want you to leave with some relevant message, relevant understanding. So these are the 7 investigations you could use tomorrow if you wanted to. They're all free. They're all on the website. just go, check them out. They're aligned with common topics that you all would teach in an intro astronomy course. These we have found to be very appropriate at multiple grade levels, so we don't assign a grade level from them. We have gifted 6th graders that do well, and we have the Astro 101 college students who do great too. And so anywhere in between seems to work okay. And I already kind of mentioned this, but we are in the process of converting all of these to Spanish. Right now we have 3 out of the 7 in Spanish. In addition to that, we have a lot of support for teachers. So if things aren't working right, or you want to learn more or get more training, we have a pretty aggressive professional development program. And we have a citizen science program in the works. Now, we are not going to be developing citizen science projects. We are going to help scientists develop citizen science projects. We anticipate there are going to be hundreds, if not more than 1,000 citizen science projects coming out of Rubin, all different sorts of sciences. So what we're going to be doing is we're going to partner with Zooniverse and use their platform, and we are helping the scientists get their programs up and running, not making them on our own. In addition to that, before First Look comes along, and I'll talk to you about that in a minute, we have some new products we're working on, a Summit status dashboard so you can see what's happening at the Summit. We have a Sky Viewer and Orbit Viewer tool that'll be coming out also to display data. Now let's talk about the most recent construction updates. Yes, we do have a Lego set. If you are an aficionado, it's going to cost you big bucks because there are quite a few pieces in it, but we have one that's in design. Much more complicated than this. You know, you can take things out and move it around. Right now, we installed our commissioning camera on the telescope. The whole telescope is put together. Within days, you should hear something about our first views through ComCam. This camera is much smaller. You can see only 144 megapixels instead of 3,200 megapixels. So we're going to be using this to optimize the system and learn about it before we put the main camera on, which will probably happen like January-ish. You know, you never know in commissioning how things go. But that's kind of what we're pointing at. And then once we get the main camera on and do some commissioning with that, we'll take our first images. And so just key dates for you to remember. Right now we're looking at mid-June as the time when we will announce things to the public for the first time. When do we get data? Well, the data is going to start at late 2025. It's going to take us, we're going to collect 6 months. It's going to take us 6 months to process it. So about a year afterwards, we'll have our first data release. Now, I wanted to talk to you a little bit because this might be something you want to plug into. Are you going to do a First Look event? Did you do a First Light event for Webb? You may have. So think about something you might want to do. And so just to context this is our celebratory moment to reveal our first images. It is not the point where data is flowing. And this is kind of an interesting thing that we at the EPO team have been talking a lot about. So there's a Hubble pretty picture, and there's a Webb pretty picture. And then Rubin, it's not going to be prettier. And this telescope is not supposed to be just another pretty picture. And what does it really mean to our students and to our audiences when we talk about these first images coming off? They don't necessarily have the context to understand the science of it, although certainly we can easily unpack it for them in terms simple to understand. But people tend to fixate on what they can see in the picture. And Rubin pictures probably are not going to be as pretty as Webb pictures. But we're going to win in other ways. So I want you to think back about the starts of some of the most well-known telescopes. I'm putting us there kind of just ambitiously, that people will know about us once we start making things happen. You see, I gave Hubble just a little correction there. Now I want you to think about the starts of things, and some of you were alive before 1983, so you'll understand this. When the internet got started, when Google got started, when the first smartphones and iPhones came into being. And in the beginning, people are like, oh, okay, something got started. But over time, people began to realize the huge impact this was in changing the culture of our world. And that's the challenge of a first look. It's the start of something big. It's not the something big part. That's going to come years later. And so it's something interesting to think about. How do you communicate that to people? So what will we discover? Well, probably a lot of objects in the outer solar system, a better understanding of dark matter, the better understanding of our galaxy evolution and composition, a lot of different kinds of objects that go blink in the night. And in addition to that, what haven't we talked about? We are going to find what scientists call unknown unknowns. There's things we haven't even conceived of, and we won't until we see it. We're going to find that some of the data will disrupt our commonly held theories about things. Scientists get very excited about that. I was talking to a cosmologist who said, I really hope that this just blows away our theories now and causes us to rethink things a little bit. And then asking the questions we don't know how to ask right now. These are things that it's just kind of hard to communicate, but I would love your help in thinking about that and how do we communicate that to the public. Can you help me out with one more thing? Audience participation. Twinkle, twinkle, little star, how I? What you are. Thank you. Keep wondering.
Thank you very much, Ardis. That was very enjoyable, very exciting. Just a word on our schedule, folks. We have about 8 minutes that we can take a few questions. So I will try to run up to you. If you have a question, put your hand up proudly, and I'll run up to you.
And I'll be happy to stick around if anyone else wants to speak with me, or you can see me on Friday, too.
Thank you. Ardis has a fabulous talk. Okay. It really brought me up to speed, and you're just doing fabulous work. I'm Jim Schweitzer, and I've also been on COMPAS, the AAS committee on satellites and that sort of thing. So there's going to be 10,000 low Earth satellites. How are you going to see through all this traffic? How are you going to deal with it? And it's going to be much brighter than your limit, right?
Yeah. That's a question many people ask. And it will only get worse, right? We have no control of what gets launched into space. So our strategy has been, well, we're going to have to eliminate the streaks, and we just lose the data behind it. But our strategy also has been working with numerous companies to try to do things. Like, for instance, put different reflective coatings on that reflect less light down. Alter the height of the low Earth orbit so it's not in our path as long of a time. Some satellites are rotating at certain rates that we can change that will help with that. But really, it's a whole host of things, and many of you probably know we created the Center for Dark and Quiet Skies to deal with some of these things. And so it's a big issue, not only for our telescope, but for every telescope that's on the surface of the Earth.
Okay, we have a question, and yes.
Hi, that was a great talk. Thank you. In my experience, one of the most one of the things that people seem to really, really enjoy in my dome is when I turn on the big galaxy surveys and the whole just awe-inspiringness of it. And I was wondering if we could play that really awesome phone game with the people in our dome, because I think they would really resonate super well with that.
Yeah. It's available to use however you want. I should mention everything we do, because it's government funded, is absolutely free and Creative Commons license, including all of our downloadable teacher materials that you can use to customize different kinds of assessments and all kinds of things. So,
I have a question about how scientists might access the data. So you talked a lot about that pipeline, and I heard the Rubin telescope described once as an open source telescope. Can you talk a little bit about how that data will be available to scientists?
yes, I'll talk about it briefly in two ways, because I'm not sure exactly which way you're thinking. So first of all, many countries of the world have what we call data rights, and the data is available to them immediately. For the first 2 years, they are the only people who have it, and then it's global access to the rest of the world after the first 2 years. And many of those countries have done what we call in-kind support. They've been working on part of the construction of the telescope. In fact, I have a picture here I can go to very quickly. One more. Yeah, there you go. They give you an idea of the global overview of what's happening right now. The other way that you might be thinking about here, Renee, is like, how do you access the data, right? So the alert stream, we're going to produce millions of alerts per night, and they're public accessible, but it's only like a thumbnail, and it doesn't have a lot of information on it. But they're public accessible immediately, no wait for 2 years. But if you want to get actual hardcore data, how most scientists are going to access it, maybe all, is through these brokers. And so if I'm a supernova scientist, I'm going to go to a broker. I'm going to filter that broker to look for data that I'm interested in and take it from there. But this idea of I'm going to download a set of images or I'm going to download a chunk of data, there is too much data. And it's just really hard to impress upon people how much data there is. So these brokers are going to be invaluable.
Oh, one more. Last question.
Hi, thank you. I want to say first, I did meet Vera Rubin as an undergraduate at a AAS, and she was exactly like that video, and so gracious and wonderful with her time, and that's why I got so excited when this is named after her. But I do have a question about that data, because you said that all of the naked eye things would overwhelm the camera, like it saturates it. So how are those handled on these images that are as big as constellations?
Well, I keep asking that question. I think, first of all, the images are like top secret that are going to be, there are like a handful of people who know what the first images are going to be and where they're going to be. So my understanding is they'll mask them just like a lot of surveys do, like with a horizontal bar across them. But we do lose the data like in that area because it's saturated.
So is there like a map then?
I believe so, but again, I don't know if it's like a subtraction process or if it's just like a little bar they're going to put across it. I'm just not really sure. Pardon me?
Sorry, they saturate the detectors though, so that it's not like subtraction like the
Yeah, I don't know. I have asked that question like for 7 years, and I haven't gotten an answer yet.
Let's all give a big thank you to Ardis for her wonderful talk. It was super informative, and I think all of us probably came away with something specific that we will be able to use in our institutions, and that is so appreciated because she did her homework to make this talk be useful to all of us, and it's recognized. We appreciate it. So just a word on schedule now, folks. We have up next is sponsored demonstration / break time. So if you are in the red group, you're heading to the planetarium, I believe. Let me just use my handy pocket schedule here. Okay, thank you. If you're in the blue group, you are going to the planetarium to sponsor demonstrations, and that means the red group. It says lobby, but it really just means break. So you can go to the Art Museum galleries. You can just take a break, but don't go far, please, because in just 30 minutes, then you will go to the planetarium. So hang out, take a break, visit our galleries, find the amethyst, if you haven't yet, and then switch. And then we will have dinner in the museum's auditorium, which is downstairs tonight.